So everyone, our last speaker is Dr. Hamid Bateni. He is an associate professor and the chair of the admission committee in the physical therapy program. And he will be today talking about his latest research on balance and postural control.
Okay, well, good afternoon, everyone. I guess this topic is going to be a little bit different. I hope it's not going to be boring. I also went through my slides. I truncated so many slides, so I hope that it turns out good. I'll do my best. My interest has been for the past, well, I started doing research about 25 years ago. For the past 2 decades, my interest has been mostly postural control and balance. So I picked up basically 4 research, 3 of research that were done before, and that I did before, and then the 4th one, the ongoing one, to show you guys a trend of where I am going and where I'm coming from and where I'm going. I started my undergraduate degrees in prosthetics and orthotics. I don't know if you guys know what it is, artificial limbs and those kind of things. But so I started my research with that, but then about 20 years ago I switched to this topic. Basically, and I'll show you a couple of videos to tell you what made me amazed by this one. There are some statistics that why falling is important. It's most of us have someone in our relatives and older adults who have fallen once and they faced severe consequences. But my interest triggered by this video. This was a study done by Jeff Burney and Pam Holliday in Toronto at Center for Studies in Aging. In those days, they installed a camera in a nursing home, and as soon as someone would fall, they would go there, they would call them, and they would go and change the tape. So I ended up having quite a few tape, and I extracted a few falls in it because my interest was that why do people fall? And if we can answer that question, it helps a lot. Now, I have showed this video in quite a few presentations before. Whenever I see it myself, I still feel bad for those people who fall. Now here, as you can see here, one person is falling. Then this old lady, it's not very clear because of the quality. Now she's walking, and then she's falling again. Someone coming out of the elevator is falling. Now this is probably one of the rarest video. Now today that we have a lot of security cameras here and there and a lot of video clips shared on internet, you probably find a few real videos. But in those days, this was the one video that of real falls. We have simulated falls in a lab, in a laboratory setting, but these were actually real ones. Now this gentleman put on his coat over his head and then he starts falling. One of the things that made me very much interested about again was that a lot of these people that you see that are falling, they are holding an object and they don't let the object go. There are studies showing that if you have your hands free and you just put your hand on the floor or hold on to a wall, it can actually prevent a lot of consequences. It can be a very simple fall without consequences. But like that lady that you saw, it was actually, she was falling and holding her purse, something that does not really help her at all. And some of these people were falling with walker or cane, and then you would see that they were still holding the walker and cane. So part of my study was, one of the study was, does use of walker and cane always benefit us, or sometimes it may actually work against us? Then I wanted to know why people fall. A very simple notion is that if you have an object, you can define a central mass for it. If I have this object like this and move it, as soon as the central mass goes out of the base, which we call it base of support, the object falls, right? But we as humans are not like that. If this person is standing at central mass, and then the central nervous system that controls the position and the base of support, but we do it differently. We actually purposely move our central mass out of base of support when we walk. The important thing, the problem is not the central mass being out of base of support. The important thing is, can we hold it? Can we bring it back again? Can we control it in a stable condition? As you can see here in this picture, that happens to all of us when we're running or walking. The central mass is outside of the base of support, but this person doesn't fall because she can control, or he or she can control it to get back to the position, to the stable position. Then, what do we do when the central mass is outside of the base of support? We basically do two mechanisms, two reactions. One of them is called fixed support, and the other one is change in support. The fixed support is happening when the perturbation that happens to us is not really significant. Like when you're standing on a train, or and the train starts moving, or in a bus and the bus moves. You just wobble around, but then you control your position. That would be a fixed support reaction. The other type is a compensatory reaction, and that comes naturally when we're about to fall. The perturbation is long enough, I step forward first, or I grasp something that is around me, and that would be the two conditions. So now this is an example. This is of a 73-year-old woman standing on a forced platform. This is a laboratory setting simulating a reaction when the platform suddenly moves. And you can see that she does both. She actually, now all these participants, these are study participants, they were always having safety harness, so nothing was happening to them. But then you notice that she actually performed both, so stepping and grasping reactions. Now, so that brought us to a question that for a person to fall, we need a balanced disturbance. We also need a failure to recover or perform those compensatory reactions, otherwise everything will be fine. And that, if we fail to do that, that can bring us to a fall. Let me pass through these 3 slides. There are different types of perturbation that we can actually experience. But I just, I'd like to tell a little bit about this. That tells us what we do when we're about to fall. Everything is sort of simplified here. But we have a musculoskeletal system that controls us to prevent us from falling. Now, we also have a sensory information. Basically, it comes from visual, vestibular, which is the inner ear, the same type of sensation that if you start running, turning around yourself and you stop, you see the world is turning. And then we have proprioceptive or cutaneous sensation, or some of the sensory information that tells you where your foot is, so you're planning for it. Now, this system provides information to our central nervous system. The central nervous system, we can put everything in this jargon, our processing system, our cognition, and that would send information back here. Now, we can have a feet forward or feet back. Sometimes feet forward is you hear a sound, you expect a move, then you actually control yourself, hold onto the table. As soon as the light goes off in a room, you start touching the wall. That's going to be a feedback, basically, from the light being lost. Now, each of these places can be actually perturbed. You can experience perturbation usually. Diabetic patients usually have a low sensation and they can fall because of that. Now, the sensory information can actually, the central nervous system can actually not process well, or musculoskeletal system can actually have any problem or experience any perturbation. Just same as if you're standing in a train or you walk over a slippery floor, you can fall. So what I wanted to know in this study is whether use of, now, my focus to narrow down the question was being focused on mechanical perturbation and if usal mobility aids could potentially work against the person. In one study, I wanted to know if it prevents us from. No, the reason, another reason that kind of was mind teasing and brought me to these questions was there were studies actually at that time. There was one study being done in Ottawa, Canada, showing that people who use walker and cane, they actually fall more often, which was at that time a lot of people were surprised. But the question was, we don't know if these people are falling because of the walker and cane, or they would have even fallen more often if they were not using the walker and cane, right? So that actually brought us to this question. Let's see if it actually limits us for any of the reactions that we need at the time of fall. We actually had several conditions. We gave participants a walker top, which is task irrelevant. I just wanted to have the hand in a position so that would waive the question of the hand, if the hand were free, so that's why the person didn't fall. And walker, nothing, came top. And then we perturbed the balance. People were standing on a force platform. These are, we inserted load cells on walker and cane to monitor the load, EMG, and then the platform was moving. What we did, that's only focus on the foot movement or compensatory stepping reactions. This is what we actually, this is a result or a typical trials. As you can see, this person is holding a walker top now, and the platform moves. This is how the feet are moving. They hit the cane, but still they perform sort of limits. It gives them a warning that this is the cane, sort of limits. But when it comes to the walker, as you can see, they collide, but they cannot perform. Now think about this, that at the time that they actually need the stepping reaction, they may not really be able to perform it. So overall, we experienced a very high rate of collision with the device with walker and cane. These are the type of stepping that people perform as has been classified in literature, and we looked at all of them. Now this picture basically compares the mediolateral and anteroposterior, is the next slide, of the distance of the compensatory reaction or the foot movement. And as you can see in all of them, when the object were being held in, when the walker and cane were being used, it sort of limited the stepping reactions. And then we also documented a different, this is an example of a, when nothing is, or a cane top is, or walker top is being held in hand. That's how the foot moved. And then when the walker was being held in hand, these are being basically assessed using a motion analysis system to accurately come up with that. And then another reaction or a strategy that people were performing is to walk out of the walker and still perform the stepping that they wanted to. So this part of the study actually led us to the fact that it actually limits the stepping reaction. So that would be one potential side effect of using walker and cane. Now in the other part of the study, now I wanted to know if you're holding an object, the same thing that we saw in the video, would you let it go at the time of the fall or not? And if you wouldn't, like that can be a cup of coffee, it can be a bag or anything. If you're about to fall, would you let the object go or not? And if you do, does the value of that object play any role? If you're holding a cup of coffee, you wouldn't, and a book, you would throw it. I just wanted to know if the value would actually have any role to play. And then prior activation, if you are actually having a cane or you have an activation of the hand, would that help or not? I just quickly go through it. That's again another subject. Now this time the person again holding cane and cane top, cane with load as well. And then we had now in order to force people to grasp or fall, I put actually large block of foam in front of them, so they couldn't really stand up with the stepping, right? They had to either grasp the handrail that was installed next to them, or they would fall. And now this is what happened when people were not holding an object, they just immediately went for the handrail. Now these are the foams. The picture was not clear. Or when they were holding an object, now these are the foams around the person, and this is the handrail. When they were holding the object, they wouldn't go for the handrail. Now this person was falling. They used the whole safety harness to hold themselves back.
They would have fallen.
Right, they were actually, we have a safety harness. They were using the safety harness, but they still wouldn't go for the handrail. So we ended up actually noticing that it actually it has a significant impact. We also noticed that people performance strategy often not really helpful, and that would be trying that would be trying to grasp. They know that it is important to grasp, but still they wouldn't let the object go. So that wouldn't be often. It wasn't a very efficient grasping. So still they would fall. They would use the harness, but then they wouldn't let the object go. Now another very interesting outcome of this study was that one could say, well, this person knows that the object in the hand must be held, so they wouldn't let it go and they were falling. Now, but we were collecting EMG, or electrical activity of the muscles from the deltoid, which would show if this person is actually thinking to go for the handrail, but decide not to do it for the object or not. Now, what we found out, as you can see, I'm sorry, I might have, right. So the hands-free and cane top. So the cane top was a task-irrelevant object. You wouldn't be able to say that this is, they wanted to hold on to it to control their balance. Now, as you can see, the blue line is the EMG activity of the deltoid, deltoid, or biceps and deltoid, when the hand was free, so the hand actually moved. But when you see that for the time that they were holding the object, the EMG was dead. That means that the central nervous system didn't even bother to command that you need to move. It was just flat. Now, that brought us to the conclusion that apparently our central nervous system do not like to leave an ongoing task to go for a new task, even though if that task is bearing a lot of consequences. Now, that means that it doesn't matter what object you're holding in your hand, we're going to fall holding the object. Now, that's again the outcome of it, and then now our results basically led us to believe that there might be some consequences of using assistive devices, so it is not just let's use it, nothing can go wrong. If someone needs it, it makes sense, but if they don't, then we have to be careful in providing that. Now, that led to several other studies that I'm skipping over. And this one's much newer, that I wanted to know if now physical therapy treatment for balance and postural control is usually very expensive, and it is not always accessible. Now, a Wii gaming system was out in the market, and kids were interested to play with it, and I wanted to know, can we actually use something like this for people to practice at home with a $100 piece of equipment? They do physical therapy treatment that they have to pay a lot for it. This is the design of the study. We used a scale, very balanced scale, and one of the games in Wii as a measurement tool, and we had people go through 2 sets of 6-week training. We had 3 groups of people. One group would go through only Wii training, the other would go only through physical therapy training, and the third group, or the middle group, would go through both Wii training and physical therapy training. The outcome of our study, I'm sorry if my slide is not very clear, the outcome of our study in short showed us that physical therapy training would actually do, with combination with Wii, does the best job among all these 3. And PT, or physical therapy training, in-person training, does a good job, but Wii alone still has some improvement, but not really as much as the other ones. One of the studies that I skipped before, I wanted to know also what does the sound, because we all know visual can play a role, vestibular information can play a role, and sensory information can also play a role in control of balance. But we haven't really paid enough attention at what sound or verbal cue or audio cue would actually do to us at the time of, it's funny because just this morning I came across a publication in Nature saying that that audio cue actually helped people to have a better control of their balance. That was very new. But literature in the past actually have neglected to focus on this particular topic. A few years ago I did a study. I played just white noise on people standing on a balanced platform, and wanted to know if just simple white noise. I mean, we always have to start from the very early step and build on it step by step. So this one was just a very simple white noise. Would that impact control of posture? And the outcome of it showed us that it didn't, even when we published that. But it didn't really play any role, any significant role. But now I have started, I'm sorry, I couldn't really fix these videos, but once I play them, it seems that they work well. Now, what I am doing now, my next step would be use of virtual reality in terms of training and also assessment of balance, both systems. A lot of people have started doing that recently, but when I was doing my postdoctoral at the University of Maryland many years ago, we purchased a virtual reality system over $1 million. That was very expensive. It was new and very expensive. But now you can actually buy an Oculus Rift for a couple of $100s. So my interest is, can I actually replace it with that? And if I do, can I use it for assessment and also treatment? But there are a couple of things about Oculus. Number one is that you're adding a weight, and you're also having a lot of wires. Now that wire thing hopefully is going to be soon taken off with wireless connections, but wire itself can actually provide a haptic cue that can affect balance. Another study that was done a while ago shows that if you have a very simple touch of an object next to you, it can actually influence your control of posture without any load or anything. So now the other thing, then after that, I thought, so what about the quality of the sound here now? Do I really need to play the sound at the same time or not? And if I do, does that sound matter? So we designed a study. This is started like about 6 months ago, and I haven't been able to finish up the analysis, otherwise I would bring you the result on it. But what we did, first of all, I want to know if that 470 grams of weight that you put on your head, would that affect? So there are the condition of no Oculus and yes Oculus device, and both of them with eyes open and eyes closed, to sort of augment the condition or make the condition more challenging to tease out any potential differences between these conditions. Then, when people are wearing Oculus, we also define several other conditions. Number one is with the sound, which is that comes with the virtual reality. Then no sound. Then we thought, what if someone keeps reminding you that this is not real? So we cut off the sound. Another condition was someone is standing next to the subject and keep telling them, hey, this is not real. By the way, the people were sitting on a roller coaster in our study. Hey, this is not real. Don't believe it. That sort of thing. We had a few sentences being repeated. But the next condition that we thought, what if we don't have, we have a cognitive demanding task or sound played for these people. The reason for doing that, have you ever noticed that if you're sitting in a car and your audio or tape is loud and you're looking for an address, you turn it down automatically because you don't want to waste your cognition because of that. If you see a few older adults are walking together and they're talking really happily, as soon as they get to some uneven surfaces, everyone goes quiet because they don't want to consume the cognition so that they can focus on their control of balance more. Now, this time we thought that what if we have a cognitive demanding sound played to these people? So we decided to play a story of Harry Potter to these subjects. And they didn't know that we weren't worried about how much they remember, but they thought that they need to remember the story and tell us later. This is as far as I have about this study, but I can also show you the videos if it plays on me here. This is a sample test. This is my lab. This is the video being played, roller coaster, and this is a young adult participants. And this is the video they were presented to.
So they didn't have audio?
Now, there are different conditions. Now, this is just a video of the clip of the video that we presented to them. But we had conditions of no oculus, eyes open, no oculus, eyes closed, with oculus, eyes open, and watching the oculus always eyes open, but then watching a virtual room that nothing moves. Oculus with a blank screen, and Oculus with roller coaster, no sound, or Oculus with roller coaster with a distracting sound of keep reminding people that this is not real, Oculus with its actual sound, and also the last one, the Harry Potter story. So we had 8 different conditions. And then we tested 20 young adults. The reason that I always start on young adults is because you want to take that potential effect of aging from the study. So we start with young adults, and then I'm at the middle of the analysis of the data, and hopefully it is being followed with other participant populations.
On that last study, is there any movement on the platform, or are
No.
they just?
No.
Do they really get affected and sort of?
Yes. Well, they're wobbling. When we were doing the test, I had to actually throw out some of the tests because they had stepped. We don't want them to step as well. So I had to throw out some of these tests. But we don't have, this is one direction that we are going. But we do have, I have actually several other studies going on at the same time. We don't have a moving platform, but I actually have weight connected to people, and use of computer, I control these weights suddenly drop, and that sort of is simulating a perturbation to the central mass. And then I'm going to be studying that. I have 3 other studies at the same time going on with that idea, and I also am having 2 senior projects from engineering students, and one of them are building a moving platform for us. Here at NIU, I still don't have a moving platform, and that's how I apply the perturbations. Hopefully, they're going to be done by end of this month. And that's what we're doing. Let's go ahead, please.
So I found it really interesting that when faced with the choice between continuing to hold something or to fall, people would continue to holding because you think that evolution would have taken care of that.
What?
Like if
Drop
there's-
it.
Yeah, like so that led to the thought, what historically or prehistorically would we have been holding that was so important that we couldn't drop it? Which
Or maybe our central nervous system or our processing unit, I would say, or a computer. Well, technically, the fact that you keep hearing humans are multitasking, it is not quite accurate. We are not really multitasking individuals. We just have ability to quickly switch between tasks, right? When we get older, it is going to be more difficult or time-consuming to switch between tasks. That's why older adults actually cannot perform or cannot. They're suffering from different aspects, and one of them is also that they cannot send the command as quickly as a young adult to control that. Now, throughout that process, maybe and that's what our conclusion is. Our central nervous system do not really let an ongoing task. It is not really a matter of decision. When we look at the EMG, that means that our central nervous system is so much focused on like ongoing task and would not like to let it go because you don't really have decided to let any objects go. But when something comes up unexpectedly, we are not willing to stop that and go to the other one. Another study within that route, and that's very old actually, I was part of it. We wanted to know now what will happen when we start a study, because a lot of falls happens when we start walking. We start planning where the foot comes. For each of these steps that we take, we actually plan for it. Now, when we trip over something, the only reason that makes us fall is because our plan is now messed up. I was thinking to put the foot here. I am moving my central mass with calculation that if my foot lands here, I am going to be okay. Now I trip over something, and that prevents me to land the foot at the place that I am planning at the time that I am planning, right? Now, our question was, how long do we have to be in this plan to be able to change it?
To follow up on the baby thing, I just wonder if there could be a difference between men and women and their willingness to let go of something, because
no, we didn't actually. We didn't find any gender effect on these studies, but typically, yes, women don't let their purse go. That's very common. But then men also don't let any object in their hand go. When you are not certain that you are able to control yourself, you would rather fall forward than backward.
Okay.
Backward falls are always scary. That's why you see a giant person walk like this, because they are worried that if they fall, it's better that they fall forward, not backward. You see a similar posture in people who have paralysis of some of the muscles, gluteal muscles, and that would again, they do the same thing. They would have they get a posture that if they fall forward. Having said that, though, the studies have shown the worst type of fall is actually not anterior. We don't really fall very often posteriorly. But then the worst type of falls are medialarily. When we fall to the side, that's the worst type. Those are the falls that usually lead to the fracture of the head of femur or the neck of femur or the bone in the thigh. And that can actually lead to hospitalization and everything else. In the old days, there were quite a few studies showing that you would barely remember what happened to you when you fell. We speculate, but we barely remember what happened. That's why a lot of the studies that ask people, so what happened? And they document that and do the analysis, are suffering from that source of bias in their data. But you don't remember. Now, we tend to ask that question. Of course, it's another piece of data, but it has a good chance of bias. Not to mention that some people ask, like, 2 years ago when you fell, what happened? You know, that's even worse. So we can't really trust on what happened to you or how you felt at the time of falling, right? That's another source of bias. Yes. Any other thing? Good. Thank you very much.